Hey guys, let's work on titrations now for acid bases. This is basically a lab technique where we're going to add a known amount of one substance to a substance that we don't know. But we use the reaction between the two to figure out the parts that we don't know yet. So basically, we can find the concentration of a particular solute in our solution by reacting it with something that we know it reacts with. We're going to have to use a standard solution to do this. That means one of our substances, we know exactly what we have. So we typically have to standardize either our acid or our base before we can get good results. But really, these are not limited to acid-base reactions. We can do precipitation reactions or redox reactions with these, and you're going to do redox titrations and acid-base titrations in our class. So let's look at how do you know when you've added enough stuff? How do you know that the reaction is done? Well, for a titration to work well, then you have to have equivalent quantities. So depending on the chemical reaction, suppose we have sodium hydroxide and hydrochloric acid. That's going to be different quantities than if you had sodium hydroxide and sulfuric acid. Why? Well, because the stoichiometry is different. You're going to need twice as much to neutralize a diprotic acid as you do for a monoprotic acid. So when we're talking about equivalence point, we don't really mean equal amounts of each substance, of each reactant. What we really mean is whatever it takes to neutralize that substance, right? So stoichiometrically equivalent, not just equal amounts. And to tell when it's done, we use indicators. An indicator is something that changes color when you get to a certain pH level, or maybe the reactant has a color and the product doesn't, or the color changes when it goes from a reactant to a product. Those indicators are really important to tell us when the reaction has finished. So we want the end point where you see the color change to be as close as the equivalence point as close to the equivalent point as possible. Let me show you what I mean here. Sometimes they're not exactly the same, and here's why. There's a range of pHs over which colors will change. The one that you've seen in the lab is this phenolphthalein. We said that when it turns pink, then you've neutralized all of your acid and it turned to a base. Okay, but that would happen at a pH of 7, right? Which would be right about here. Look, that's still colorless. Technically, where you see the faintest pink, that's beyond the equivalence point. Phenolphthalein is still commonly used because it's pretty close. And for what we're doing, it's close enough, but not for every reaction we do. Bromothymol blue we used with our carbon dioxide demonstration, where you blew carbon dioxide into tap water and could see the color going from blue to yellow. But this one would be hard to recognize at a 7 because it's really hard to tell the difference between blue and blue-green. So that's not a very distinct color change. So you'll have seen a demonstration or done a lab that shows how each pH indicator changes color at a different range. What complicates this too is that some of them have 2 changes. So in the acid-base range, there's one color change, and then in the base range, there's a different color change. So that can be a complication where you'll see a flash of color as it passes this point, and then you'll see another color show up later on. So let's work out a problem where we might be doing a titration, and now how do we do the math? How do we know the quantity or the molarity? So here we go. We're going to start with a balanced reaction. So let's inspect this. Looks like we have a diprotic acid, so we need twice as much base, right? What's the molarity of a sodium hydroxide solution? So we're finding concentration of NaOH, and for simplicity's sake, I'm just going to call this OH because nobody wants to hang out with this guy. Nah. and we had 48 milliliters of this stuff that was needed to neutralize 35 milliliters of 0.144 molar sulfuric acid. All right, well, for us to solve this problem, we got to go to moles. And the easiest way I know to get to moles is volume times molarity. So we have 35 milliliters, and then I'm going to call molar my millimoles per milliliter. So there's my sulfuric acid. And now let's use our mole ratio. For every 1 millimole of sulfuric acid, how much base do I need? 2. Stoichiometry says so. So 2 millimoles of sodium hydroxide base. And we're not done yet because I want to know the molarity. I need to know moles over liters or millimoles over milliliters. Here's my milliliters. Here, let's put that where we want it. It's got to be millimoles over milliliters. So we'll put that down here. And we've set up our t-table so that all we have left is molarity. Millimoles per milliliter. Good. Well, time for a calculator. I've got mine, and I sure hope you have yours. So 35 times 0.144 times 2. Then we'll divide that whole thing by 48. So I have 0.21 molar hydroxide ion concentration, or we could call this 0.21 molar NaOH. Right? Put a box around your answer, and we're all set, ready to go. So when in doubt, go to moles, just like always. Let's do one more. Example 2. The quantity of chloride ions in a water supply is determined by titrating the sample with silver. You know what will happen there, right? Silver and chlorine make silver chloride, which is insoluble. Silver is one of the 3 amigos. How many grams of chloride are in the sample of water if 20.2 milliliters of 0.1 molar silver ions is needed to react all the chloride in the sample? All right, let's work it out. We got to get to moles, right? That's what we do. So start with volume, and let's go to moles. Volume times molarity equals moles. So I have 0.100 millimoles per milliliter, and that was silver ions. And this is easy because it's a 1-to-1 mole ratio. For every millimole of silver, I need exactly 1 millimole of chloride. All right, and grams is our target, so let's change moles to grams. And how about millimoles to moles? So mole is bigger than millimoles. There's 1,000 millimoles in every mole. Now let's do moles to grams. 1 mole of chloride ions is a mass of 35.45 grams. You'll find that on your periodic table. And it's not chlorine molecules, so it's not Cl2, it's just chloride ions. All right, I think we're all set then, huh? Yeah? All right, good. So 20.2 times 0.1, divide by 1,000, and then multiply by 35.45. Watch your order of operations when you do this. I would be showing you on the screen if I had a calculator installed. Soon I will. So if you're not sure what keystrokes I did, check with me in class. Let's keep 3 sig figs here. 1, 2, 3. So we get 0.0716 grams of chloride ions. Now ask yourself if this makes sense, because that seems like a pretty small number, right? We had a water sample, and we're looking for chloride ions. It should be a very small amount. Otherwise, we're not going to have very good health if there's too much junk in our water. All right, looks good. That's how we do titration problems. You just work out a t-table, starting with the volume and the molarity of something that you know, and then you work it through to get your mole ratio to the thing that you don't know. And we're going to have lots of practice at this. Good luck.